Okay, let's start. Are you also recording? Good, we are also recording. May I have your attention? Full attention, please. Today's topic is about FIR filter design, and I really need everybody's attention here. I'm warning, I have a wet sponge here, and I'm pretty good at it, so. Okay, good. So first, before we go to this filter design, one clarification of the frequency mapping of digital systems, complex plane, and more or less everything. So last week we had the a topic about the frequency response of a LTI system. So linear time invariant system. So we are talking about the system which has a the difference equation, something like this. Oops. Yes, correct. Bk x n minus k. So this is the difference equation, which means that then the transfer function would be h of z equals to basically the same sum, except instead of x of n minus k, we have z to minus k here. And on the denominator, there's a ak times z to minus k. And here k goes from 0 to n on all of those sums. And there is also, okay, roots. Nth degree polynomial has n roots. So we have the product form k starting from 1 to n, and then we have z minus z k, and those are the 0 points. Here k1 to n, z minus pk, and then there's a constant, basically b0 divided by a0 and the beginning to have the same scaling. Okay, so basically when you are deriving or describing or designing a system, you need to figure out what are the system parameters A and B. Okay. One, what I noticed a small problem on the exercises was that sometimes, for some reason, A0 goes to 0. It's never 0. A0 is usually 1, which comes from the fact that usually the difference equation is derived from a equation where you have the yn on the other side and everything else on the other side. If you have a0 as 0, then you wouldn't have the left-hand side at all. You cannot then calculate any yn there. Okay, so that's one noticeable thing here. Another, basically, now this frequency response, complex frequency response that we can calculate by actually calculating the transfer function at unit circle, j times omega. That's the frequency response, and it has the amplitude response or magnitude response, just the absolute value of this part. And then we have the phase response e to j times theta of omega. Okay, the phase response. Now, a lot of questions about the omega here. So here it's more or less arbitrary frequency, since I haven't put any real frequencies here yet. But for example, if we do frequency analysis of the system, let's not. Okay, I'll leave that one there. Or frequency analysis, spectrum analysis of of signals. So Fourier spectrum Pxx of some signal. And here's our normalized frequency omega or physical frequency f. They basically are just, there's a one simple scaling factor in between those numbers. But we have a sampled signal, which means that on sampling rate over 2, or actually, okay, physical frequency sampling rate over 2, which is actually what we call Nyquist frequency f of n. Okay. So for example, 2 kilohertz sampling rate, this would be 1 kilohertz. That's actually the same point as our angular frequency omega equals to pi. Where that pi actually comes from. Let's draw the complex plane. Imaginary path, real path. And actually that omega could be, for example, here. That's simply the angular frequency. And now if we tie this one into this system level, if we have omega at pi, we still have the same physical frequency here, fs over 2, or, well, Nyquist frequency. All right. And okay, so that's basically for signal the highest frequencies that can be sampled, or for the system it's highest signal that can be represented or handled by the system. Okay, which is actually here. That's angle pi, or if we go the other way around, it's also minus pi. Angular frequencies, and physically it's actually sampling rate over 2. So then that omega here, okay, is the physical frequency divided by Nyquist frequency times pi. Simple scaling formula between the angular frequency and physical frequency. Okay. And now the question about where is the minimum amplitude response of the system. What we also noticed that part here, when you take a look at that one, it actually, all right, A0, B0, yeah, it gets a little bit small. But these values are distances to those special points. So on the numerator part we have the product of distances from point E to J omega to 0 point. So if we have a 0 point, for example, here, another here, complex conjugate pair, then if we have the signal amplitude exactly on that angle, omega, let's see, z, then this amplitude response, the numerator part goes to 0. At unit circle, point at unit circle would be something here, E to J omega. And at that point, we actually have the E to J times omega z, same angle as here. That one. Okay. And what is the corresponding frequency? You need to figure out what is the complex angle here. And then use this formula to calculate what is the frequency exactly where the minimum is. Okay, now I have given you enough of hints, I think. Okay, so that's on this system basically. That's where the minimum amplitude response or maximum attenuation is. Okay, and then I actually took something granted on the sixth or seventh exercise where I'm asking which is the frequency of, yeah, well, that is the frequency where you get maximum attenuation. Okay, we haven't actually covered what is the attenuation yet. It'll actually come to today's lectures. But on the other hand, you have plenty of time still to return the exercise, so I don't think that there are any harm done yet. All right, so that's the review of the last week. Any questions? No, not yet. You will. Today's topic is about FIR filter design. Last week we already learned about FIR and IIR system. So this is the finite impulse response system, which means that the impulse response stops at some point. Okay, but then some basics of filters first. Filter fundamentals. So first of all, how the filters are categorized, and that's roughly how it goes in the world of digital filters. So we have low pass, band stop, high pass, multiband, based on the behavior of the filter in frequency space. So this kind of filter, what I have here, would be band stop, since it actually stops some frequency for passing the system. Then digital filters, we can have FIR or IIR filter. There are also some categorization by the phase response, but that comes later. Low pass filter. Let's take a look first on that one. So low pass filter. Filter parameters, and I'll just start with the digital filter. So that's our Nyquist frequency, physical frequency, or pi at omega. Omega equals pi. A low pass filter means that it actually passes the signal at low frequency, and then it has big attenuation on the or ideally goes to zero. So this would be ideal low pass filter. It passes all the signal on the band pass, and then after some cut-off frequency or corner frequency, the signal goes down to zero. Okay. This one here would be attenuation, and usually in decibels. And well, 0 in decibels means minus infinity. So an ideal low-pass filter has infinite attenuation on stop band. Okay, let's see. And let's define something here. So this is the pass band. And then after that, that's the stop band. And here we have the stop band attenuation. and this is actually in linear scale. All right. Well, that kind of system does not exist. We always have some sort of approximation. The word is not ideal. So realistic looks more or less what I have there on the picture. So, but I need, I need to think also. So that's why I still use the whiteboard. Okay, still the Nyquist frequency, or the place where the angular frequency goes to pi. Realistically, we can have pretty flat passband and then a transition band, meaning this kind of steep edge or square box does not exist in real world. Impossible to do unless you want some bad things happening on the frequency space, the time space. Okay. Then generally we also have some of that kind of behavior on this system. Especially on FIR systems, we always have some sort of that kind of bumps. And let me put it on decibel scale, dB. That would be 0 dB, meaning no gain, but no attenuation either. Okay. Here, usually on these filters, we actually have a 0 at the unit circle to make absolutely the best attenuation ever on certain frequencies. Okay. There, the cutoff frequency is usually it's defined by where the amplitude response goes to -3 dB. So half the power of the signal. Okay. So basically, now this one defines the passband. And also the bandwidth. Okay, bandwidth is for low pass filter is same as the passband width. Width of the filter. All right, and then where's my green? On the stop band. Okay. Fundamentally, that's where the stop band is usually put, but okay. This is also something like beauty, It also depends on the interpreter of who is viewing that, where this stop band attenuation or stop band is. We could define it also here if we can tolerate that the transmission bandwidth would be wider. But that depends on the application and requires a little bit of practice to finally find the correct place for where the stop band starts and where the transition band ends. Okay. Anyways, it's defined so that okay, at certain level there's the stop band attenuation A. Notion. Okay, and where it starts, the stop band actually starts here, FSB. On that point where the stop band attenuation defined, stop band attenuation hits this transition here. Okay. And the band, well, let me. Pass band, so this would be stop band. Then we have, okay, whatever is in between is the transition band. All right, So those are the parameters. So that's the f minus 3 dB is the passband corner frequency or passband corner frequency. Okay, that FSB is stop band corner frequency, or well, there's also sometimes this is also referred as cut off frequency. That's where the system actually starts to attenuate the out of the band signals. So that's stop band corner frequency. Oops. All right. And usually the transition band, this is actually defined as a transition bandwidth. So width of that band. Okay, simple. This part, everything is simple. Should I? Not yet. I almost forgot. Pictures. I need to take a couple of pictures of the whiteboard. Just in case. That one too. Silent mode. Okay. All right. This part quite simple. Sometimes we actually have a passband ripple. So in low pass filter, it means that the this passband actually has, for example, that kind of behavior. Ripple R. Okay. 0 dB. And that would be R dB here, marked as decibels, which also means that our stop band or the passband corner frequency would be here, where that ripple starts, or ripple stops and the transition band starts. That's where the corner frequency is defined on this case. Okay, then the other filter systems. Okay, so that's the low pass. We also have high pass filter. I think I can put more than one here. So high pass filter, as simple as low pass, except of course it attenuates the lower frequency components and passes the higher frequency components. So our pass band is here. Pass band, stop band. stop band attenuation transition band. Okay, easy. High passes, high frequency components. Then we have band pass. Band pass filter, well, simple. There we have two cutoff frequencies. Cutoff frequency 1 and cutoff frequency 2. Passes here. Then it has 2. Also the stop band attenuation and stop bands. It may be symmetric, but it doesn't have to be. Okay. So again, this is the pass band and 2 stop bands. Stop band 1, stop band 2, or lower stop band, higher stop band. And the cutoff frequencies here, and also the 2 transition bands. Of course, both the high pass band pass filter, they also can have some ripple on the pass band. Okay, then low pass, high pass, band stop filter. Well, looks like this. Two pass bands, and in between there is the stop band and the transition bands. Lower pass band, the higher pass band here. Pass band. Then there's the stop band. Oh, not green, but blue. Okay. This one here is the stop band with the attenuation, of course. It has this attenuation A here. Okay. And 2 transition band here. Transition band, also 2 here. Okay, so this is called band stop. Then one more, which is fundamentally, it's a generic kind of form. It's also so-called multi-band. Multi-band filter. For example, on audio we have multi-band filter. Low frequencies, high frequencies, and middle frequencies. Right. Or discount bass and middle. So that usually this middle one is fixed, and you have only 2. So basically that goes up and down by the volume. Okay, and then you may have for the low, you have filter which can vary the this gain or attenuation of this part low, and also the higher frequencies like that gain of high. So this is just example of multiband. Tone adjust of your car radio. Seriously, it's like that. So usually say from between plus 20 to minus 20 dB is quite enough for adjustment of different tones on your car radio. That's part of human physiology, actually. And then you don't need to adjust this, since you will adjusting it by the volume from 0 to 120 dB or something like that, depending what kind of blasters you have on your car. Okay, good. So those are the fundamental filter types by the frequency response, or more specifically, amplitude response. Low pass, ideally it's a box which has a just single passband, and then immediately after that passband on the corner frequency, stop band starts, and infinite attenuation on stop band, unity gain, and the passband. Realistically, well, unity gain actually means 0 dB, but you cannot make this kind of edge with the digital filters, so you must actually take the realistically. You have some slope here for system to kind of react for the signal, and then you don't have infinite stop band attenuation. You always have some realistic number for stop band attenuation. So it means that the pass band and stop band are separated from each other, and there is a transition bandwidth in between. Okay, and filter may have non-flat pass band, and then it's called basically ripple. How many dBs it has the ripple on the pass band. Other filters than low pass, we also have high pass. Okay, so the pass band is on the high frequencies, or band pass, which has the pass band on the middle here. Then I actually need to also point out something here. Okay, bandwidth, whatever the filter is, the bandwidth is always this one here. That's the bandwidth. So whatever is between cutoff frequencies, or, well, yes, bandwidth. On band stop, the stop band bandwidth is here. So when there is a talk about bandwidth, is something that we always measure. If it's stop band bandwidth, okay, for stop band filter, that makes sense to define that one. For pass bands, the bandwidth would be defined by that one. Low pass filters, bandwidth is simply this one here. High pass, the bandwidth is here. Simply, what is the difference between the cutoff and, well, the end frequency? Okay. In this one, we would have 3 bandwidths. Actually, this one also have 3 bandwidths. Stop band bandwidth, higher port path bandwidth for pass band, and lower pass band bandwidth. Okay. Okay, good. Any questions this far? So this is the terminology. Then I take a couple of pictures and continue. Right. and go to the FIR filter design. Okay, first of all, why we would use an FIR system. Let's first remind what is FIR. FIR, finite impulse response. One fundamental reason why to use finite impulse response system is that the difference equation can be written simply like that, ek times x of n minus k, without any feedback. We do not need any feedback for FIR, which means that it's quite simple to calculate. Right. You just need the input terms and that's it. And let's think of also the what does our transfer function look like? It has this bk times z to minus k divided by ak z to minus k, and here we have only a0 is 1, other terms are 0, is simply bk times z to minus k. Which happens to be also the Z transform of impulse response. All right, so H, K is actually the impulse response. So fundamentally, we can just define this impulse response or measure the impulse response, then we can determine the system. Okay. So reasons, simple formula for output. And then this is also quite nice. Impulse response defines the previous, the simple form for output. Third one, you also can have so-called linear phase response. Last week we noticed, okay, if we have linear phase response, we actually can preserve this pulse form when the signal goes through a system. Okay. The finite impulse response systems can have a linear phase response. Do not necessarily have, but they can. Okay, and then of course one more thing was the this h of n can be measured. Okay. Then there are basically three methods that I used, but those are on my screen there. One way is the impulse response truncation. Yeah, that's nice curiosity. Another one is windowing method, which is usable way of making these FIR filters, but it's not optimized or optimal in many ways. And then there are the real methods, which are always the optimized design methods. Okay, blah blah blah, yada yada yada. One picture on the table now. So example of RC low pass filter. I made that myself. Yeah, I made some measurements. I took a simplest RC filter I can imagine. Analog filter, 1 kilo ohm resistor, 1 microfarad capacitor, time constant 1 millisecond. Okay, that's the transfer function, or not transfer function, but the frequency response of that filter would be there on the table. Okay, and then I measured the impulse response. Lab setup was such that I ran a step function from the function generator, which is on the top of that picture, and then just measured the input with one oscilloscope lead, and then I have the output on the other oscilloscope lead. And then what I did, well, I took that one on the memory stick, got it on the computer, and did some magic. Since I knew the component values, I know, okay, 1 over j omega RC plus 1 is the analog frequency response, but the digitized, I calculated the impulse response from step response. Thought, okay, this is a linear system. Then the if I take a difference of, well, it goes, this one actually goes down to the first lectures we had. So basically we have a impulse function is also same as the step function minus time delayed step function. If a system is linear, I want an impulse response, I can actually run step function in the system, and this time it was actually the whole thing was so that I had the continuous time step function that I run into this continuous time system, and I digitized the step response. So basically I was calculating the S of n step response. So that's the system output for step. Okay. And from that one, I just take the h of n equals to s of n minus s of n minus 1. And I didn't do much of damage to any mathematical law that there at all. Okay, but I was measuring the step, the impulse response. And from impulse response, I have the system. And with the system, I can calculate the frequency response. And that's what I have there. I have a comparison of the green one, which is the theoretical from analog electronics, theoretical amplitude response, and that blue one is the digitized signal and what I get as an impulse response. Pretty noisy, but otherwise you can do it also that way. with some time and a lot of coffee, I could have generated enough of information to actually match those better, but it actually never matches the system exactly. That's a simulation now. If I had infinite time, or at least 2 weeks to measure it, to get rid of the noise, I would have get something like that one. So basically, the green one is still the original, and the blue one is the measured. Well, measured, now it's simulated. And basically, with this impulse response truncation method, you always get a little bit of the at the end of the spectrum, you will get the response a little bit off, depending on the sampling rate, how much off it is. Okay. So yeah, for curiosity, it's okay to use the this kind of simple truncation method. Then windowing method. Windowing method is quite simple. There are only 5 steps and that's it. Plus a couple of more steps if you want something else than low-pass filter. We start from ideal low-pass filter. On continuous time. So I start with this kind of filter, from minus FC to FC, passband both sides of the zero frequency. So, well, yeah, I make it symmetric. These basic, yeah, the same frequencies, they have the different phase. They are complex conjugates. Okay, and I can then check what would be the system, the continuous time system impulse response. Well, okay, impulse response and transfer functions are quite, you know, related to each other, since the Z transform of impulse response is the same as transfer function. So you need to know only the impulse response. Or now we know the transfer function. We set up this transfer function so that it has the amplitude response of 1 between FC and minus FC and FC. Then we can make the inverse Z transfer. Don't worry about it, since Timo already went, so that there's no mathematicians on the classroom anymore. By magic. All right. Well, we are just using the value, the things that, well, there have been some history of people, mathematicians, physicists, doing all the jobs, so that we have all these wonderful tools that we can just use. Okay. On time base, continuous time impulse response, h of t, that's actually a constant times a sine of some x or x times some constant. Okay, this is nothing to remember, since we have, you know, some pointers on those slides. So, but anyways, its form is sinc. So it's constant times some sinc function, sinc of x. So sine x or sine pi x or pi x is the sinc. sinc of x. All right, so that's the form. It's nice to have that kind of form, since now we can do sampling. We have something to sample. Continuous time. It's easy to get it to the discrete time by taking samples symmetrically on both sides of the frequency 0k. Do I get it about symmetric? Yes. Just about symmetric. So symmetric sampling. H of n. But this is still a small problem, since this is still infinite, since this h of t goes and goes and goes on both sides. So how to make it finite? We use window to make it finite. And the simplest window would be to set these out of the box values actually to 0 and multiply these values with 1. So we have a box window. Okay, everything is fine this far. We started the ideal low-pass filter, got a z-transform or inverse z-transform of our, well, h of z, actually what we defined. Got inverse transform to get the impulse response, and then sampled it. Okay, that's sampled. Then we cut it. So we are doing truncation, impulse response truncation. And mathematically it means that we are windowing the this sampled sync. Okay. The last thing here is what to do is to actually check what kind of response we got, since we did two things for it. We did the sampling. It usually doesn't hurt as long as we get you know, the most vital information on this sampled signal. Another one we did was we did a truncation, which is something that will have effect. Okay, so we can check it by doing the Fourier analysis now. Of the system. So fundamentally, we calculate what is our h of z in real. So if this is hdz. No, not that one. H original. Okay, h of z. This actually would be the h ej omega. Oops, h of n. Okay, we get the impulse, or we get the impulse response. We get the corresponding transfer function defined by these parameters. And what we will get is something like this. It will look something like that. With given cutoff frequency, okay, we get some unidealistic parts there too. This was ideal, but reality, when we were doing truncation, we generated also a realistic stop band properties here. Stop band width and also the attenuation. But the passband is okay. This simple method will give a correct passband. for the system. Okay. Now there are two problems. One is the stop band here, the stop band attenuation is not too good. Let me take a quick look if there is a, okay, constant sound. Okay, I see there are some, even some values here. Maybe I should take the MATLAB right now and take a quick look what it looks like. Or do I have a picture here? Oh, okay, I have. That's the picture. Convolution frequency. Okay. So the attenuation like attenuation actually depends on the window shape. Now where this one comes from, this kind of a boundary kind of shape for the attenuation, it only can come from the window. So basically when we have this h times Wn, and this part produces this box, back to the box, and this window produces the rest of the these features what we can see. And so transition bandwidth and the stop band is produced more or less, well, only from this one. Okay, this might be a little bit heavy, but actually when you take that Fourier transform of our h of n, you are not taking just h of n, you are taking h of n multiplied by Wn. This is not the heavy part. The heavy part is here. This is the same as taking these separately. Okay. Wn, h of n, and then applying convolution in frequency space. So we are taking basically this the amplitude response part of the sampled sink, which is a box, and then we have this box, and then we have the amplitude response part of the window. And here window is rectangle, which means that on frequency space it's sink. Okay, that's funny. That part produces sink of omega something, and that part produces box. And they are convoluted with each other, meaning we are basically sliding the box and have this sink, sliding that one. It's hard to see what happens here, but basically it produces this kind of amplitude response at the end. Okay, so to get the attenuation better, we need to take a look at this sink part, or the, no, not sink part, but this window. This kind of window, rectangular window, actually produces quite a lot of high frequency component from the edges. Okay, to get a rapid change happening on a signal, when you think of a Fourier spectrum of a signal, you need a lot of high spectrum components. If you want to smooth it, you will basically start cutting the edges, so-called. Make the edges smooth. Then this kind of smoother window will give you less high spectrum components. Less high spectrum components, so you will get the increase of stop band attenuation. Okay, but on the other hand, you will lose something from the transition bandwidth. The transition bandwidth goes higher. Okay, however, there are some fundamental the window shapes that are generally used in signal processing. They are on the table. Bartlett or rectangular is never used, since it's very simple to just use any of those in addition to get much better stop band attenuation. So rectangular window gives you only 20 to 30 decibels of stop band attenuation, and that's not much at all. Bartlett window, which is triangular window, so triangular, it's just triangle on both sides. Even that one gives you already, up to 40 dB attenuation. Hanning, half cycle symmetrical biased cosine. Yes, sounds funny. Basically, it's just cosine which is raised up, so it makes a bell kind of curve. And when you're just thinking, okay, cosine, it might have a very good. So it's basically spectral, it's just one peak spectrally at half cycle. That already gives good stop band attenuation, up to something like 80 dB. Then these Hamming and Blackman and Kaiser windows and other windows, but those are the most commonly used window types. And that's how they are, they actually work. On the left-hand side, there are window shapes, and as you can see, they do not necessarily change much from each other. Okay, they are quite similar, but still on the right-hand side, we have this the frequency response of those windows using actually 100 Hertz cutoff frequency on a system. So this is windowed. There has been a sink and a window, and those are the attenuations. So as you can see, the box is the worst. It's the easiest, but it's also the worst. Even with that, Bartlett, which is not much of a window at all, which was just a triangle, you get better passband response. Then there's this, my favorite is Blackman, since it goes down like that one. On the other hand, you also see the transition bandwidth there. Okay, I must come here. So the transition bandwidth here also changes. The rectangular window has the shortest transition bandwidth. When you go to Blackman, it has the widest transition bandwidth. So it's basically a compromise between transition bandwidth and the stop band attenuation. The stop band attenuation you can affect only by selecting a correct window. Transition bandwidth you can actually affect otherwise. Couple of pictures and then I'll explain. Okay. So, transition bandwidth. Basically, it's quite simple theory. If you multiply, let's see, multiply the frequency, well, the other way around. If you multiply the time, it's same that as you would divide the frequency. Okay. So if we have a transition bandwidth like that, transition bandwidth, and you want to cut that one into half, like this. What you need to do is just multiply the time. And how do we multiply the time? Is if our original sampled sink originally was up here, up to here, window 1, you just take a wider window, double the wider window, you will get transition band shrank by the factor of 2. Okay, and there's on that picture, it's basically the same Hamming window, 100 Hertz cutoff frequency with different number of samples, also different window widths. Okay. Good. That was covered. Then, of course, we had the other kind of filters. Low-pass filter was only one of them. So, next question is, how can we actually make other window types like high-pass filters, band-pass filters, stop bandwidth filters? Okay. That ain't difficult either. We'll talk a little bit about filter transformation. Hypothetically, let's take a filter. It has a, whoops, that stopped working. Filter, low-pass filter, and just for fun, I will also draw here the both sides of the frequency space. And if we want to move that one, that filter as it is, into different locations, for example, so that the center frequency would be here. So move everything here like that. How we can actually do it? This is done simply by, okay, this is quite, it should be familiar to you from the communications class, the 101 on communication. Modulation. Simple cosine modulation. Okay, so if you have any spectrum whatsoever, for example like that, and you want to transfer it on different frequency, what you would do? You multiply that signal with the cosine and transfer that one. So it fundamentally moves that peak there. So if that is our signal x, that will be xt times cosine of 2 pi fm times t. Right. That's what modulation is all about. And actually it also, well, it's just there, but it's also at minus fm till the same peak. Okay, same thing here. If you want to transfer your low-pass filter properties to some another frequency, so low-pass to bandpass, modulate with f of m, which is a new center frequency, by sampled cosine. Okay, so we have h of n times the window shape times cosine 2 pi fm and times t s times n. Okay, that's the whole thing. Just with one reminder about bandwidth. For low-pass filter, this is the bandwidth. It's the physical frequencies. We don't think of too complex on this one. So low-pass filter bandwidth is here. But when you use the bandpass or low-pass to bandpass transformation by simply modulating it, this would be actually that bandwidth of the bandpass filter is 2 times bandwidth of the low-pass filter. Just reminding of that one. Since when you have this 0 to Nyquist frequencies, you always also have the negative frequencies, and that one comes along. So it that doesn't start with the just forget that one, and it would have very steep edge here. No, it transferred the center bandwidth here, so it has both sides. It has that low-pass filter property. Okay, but otherwise this is quite nice. Simple way of doing the bandpass filter design. If you need to have, for example, let's see, this is something I might actually write here. Example. Need, say, bandpass filter with bandwidth of, say, 100 Hertz and some other parameters. We need to start from low-pass filter, where the FC is half of that bandwidth that was required there. Easy. Otherwise, you will get too wide. Too wide bandwidth. Okay. That's easy. Although since this one is split in two parts, we also lose some dBs, so it drops the amplitude response by 6 dB. So we have to rescale the filter by factor of 2. So we need to have 2 times here to preserve the scaling, unity gain. Okay. Then another transformation is low pass to high pass. High pass. This is also simple. How about if this one was Nyquist frequency? So we start from the low pass filter again. We transfer it so that our modulation frequency is Nyquist frequency, sampling rate or 2. Well, this one is then transferred here, so far actually it goes something like this. Well, that's the other side of the edge, but okay. So now we have a high pass filter with h of n times the window times cosine 2 pi fs over 2 divided by fs 2 pi cosine n times pi. This here is actually plus minus 1 thingy. Actually, it's minus 1 to the power of n. So changing the every other term on the this impulse response will transfer that one from low pass to high pass. And again, remember about the bandwidth. Okay, bandwidth here, the same bandwidth here. Well, the same because of the same reasons. Okay. And now you just need to read carefully the filter requirements, since if the cutoff frequency of high pass filter is given, you must basically start from the bandwidth, BW. We always start with the bandwidth. What is the required bandwidth for the low pass filter to start the design flow? Okay. Then we also have that low pass to band pass. Band pass. Okay, how to do low pass to band pass filter design? Well, band pass filter is actually low pass filter plus high pass filter. Okay, simply saying if that is the low pass part, then we have another filter with different properties. High pass filter, well, adding those together is a band stop filter. Just with a reminder that these terms here will be summed together, meaning that the sum of those will make the stop band attenuation of the sum a little bit higher than the stop band of either of those. So up to 6 dB. Okay. There's also a summary. So everything basically filter design start by making a proper low pass filter, thinking of what would be the minus 3 dB or the cutoff frequency or the bandwidth of the low pass filter. Based on, well, if we are designing high pass filter, then we must actually start from that bandwidth, designing the low pass filter bandwidth. Or here on the band pass filter, we have, this one is double the low pass filter bandwidth. So if you have given a bandwidth requirement for bandpass filter, you then put that one in half and use that one as a low-pass filter cutoff frequency. Okay, and then you design the low-pass filter for given attenuation and transition bandwidth. Transition bandwidth is just taking more points into the on that impulse response, and then just at the end do the modulation, okay, or band stop, combine the filters. Okay, any questions other than can we eat now? Yes, yeah, it's a lunch break. And basically, I have a slight hope that today, when we ran a little bit later than usually, there are no half-hour lines on the yeah, there will be 1 hour line. So I think we'll better start, say, 1:15. Right. Exercises will start at 1:15. Okay, good. Thank you. Stop the recording.